What was the second one? 12 months in a year. Wow, I don't know why it sounded like miles when you guys said it. Let's just go ahead and raise your hand if you have it, and that way you can be like, yeah, I got it. So yeah, 12 months in a year. How about the next one? Joe, Jason, I said raise a hand if you have it, and then I'm going to call on you. Maybe we missed the call on you part. Joe, go ahead, because you started saying it. 31 days in December. Jason, what's the next one?
1,000 years in a millennium.
1,000 years in a millennium. Blah, blah, blah. Lauren, what's the next one? Millennium. Yeah, 1 leap year every 4 years. Is she good?
What?
Is she good? Yeah. Okay. Thanks. Bye, Patrick.
Bye, guys.
1 leap year every 4 years. What's the next one? Who has it? Matthew.
4 seasons, summer, spring, autumn, winter.
Ooh, 4 seasons. Summer, spring, autumn, winter. Maybe you would have done a little better if it was an F for fall. That works, though. Next one. Yeah, Sam. 12 days of Christmas. Ooh. Ooh, nice. What's the next one?
60 seconds.
Wait, don't start talking. Jason, go.
60 seconds in a minute.
60 seconds. I can't talk today. Good. Number next one.
10 years in a decade.
She came in late. Yes, 10 years in a decade. Then the last one, Wesley.
366 days in a leap year.
Yeah, 366 days in a leap year. It's definitely not this year. Yeah. Oh, like, is it this coming? I think it's, is it 2020 or is it 2019?
Yeah, it doesn't actually. Wait.
Mr. Richmond actually has a birthday.
Is it this year? Is it only like 15?
No, I think he's I think he just had his, I don't know. No, I'm confused. No. Yeah. I think he just turned, oh, there was some big date, and I forget what it was. He was like, I'm finally this, but I don't remember.
13 is probably 15.
Yeah, we're in there. Oh, no, you gain a day. February 29th. Okay. Question. What happens if you drop a pebble in a pond? I thought I had it, but I didn't. Aww. It ripples. So I drop a pebble in the pond. It's Velcro. Don't worry, I'll just put it back up. Me? Oh, I didn't draw this. No. I Mod Podged it on a canvas that I painted from Michael's. Anyway, this is MC Escher.
I used to stare at that in freshman year.
I think that's fractals actually. What happens when you drop a pebble? It ripples. What are those ripples called? Ripples, waves. What else moves in a wave-like fashion? Sound waves. What else? Light waves. What else? Microwaves. Ooh. Gamma rays. Oh, rays. That doesn't work. Radio waves. That still has to do with sound, basically, kind of with frequency. Okay. Lots of things move in waves. Do you? Griffith Observatory, the big. Or a grandfather clock. Sure, grandfather clock. Move. What else? A spring. Guitars, the vibrations on the strings. Yeah. Vocal cords, sound. Kind of. But hold on. How does a pendulum move in waves? Doesn't it just move back and forth? How does that correspond to this? This is like up and down, right? Okay. What if the pendulum, right? What if we have its equilibrium, kind of like a still surface of water? Its equilibrium be the center. Okay. Then it has a max displacement, this direction. Just a max displacement. You're thinking angles, that's not what I'm talking about. I'm talking a distance. So a distance, a max displacement this way, comes back through equilibrium and a max displacement that way. What happens with water in waves? Equilibrium, max displacement this way, comes back up through max displacement that way, and then comes back. Now you wouldn't see the wave necessarily of a pendulum unless you graphed how far away it is from its equilibrium or its zero with respect to time. Because if you were to graph with respect to time, you could say, oh, it's at 0, and then it goes a positive displacement, a displacement away, and then it comes back to the 0 as time is passing. Then it goes a negative displacement, then it's back, and then it keeps on going. That makes it look like a wave. Spring, the same thing. A spring could just be like sitting there, but then if you pull it from its equilibrium, how's it going to respond? Then it's going to up past, and then it's going to, yeah, boing, 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 exactly. Now, what on earth in math can model that? Oh, it's like a parabola. Oh, no. It's a few parabolas. No. It's a sine and cosine curve. Because a sine curve acts like a pendulum. A sine curve acts like ripples in water. A sine curve acts like sound waves. It needs to be amplitude? And have a certain frequency. Oh my goodness. Go ahead and pass up your reflections. We already talked about them. I'm going to grab them from you guys, and let's get into our notes. Because we need to figure out how does sine and cosine make waves. Ooh. We're making waves, but in a good way. I don't know. He's on a college visit, I think, if I remember right. Well, that's complicated. Okay. Thank you. Thank you. Thank you. Is that okay? You learn every day. Pendulums and waves and sine curves. Here we go. Question. At 0 degrees, or 0 radians, if I were to call these angles and call these ratios. I know, x and y. But if we were to call these angles, we could call them theta if you want. If we call these ratios, we can make those y. Let's figure out how sine and cosine make waves. Not just that they do, not just look at it and say, cool, go team. But how? If these are angles, 0 degrees, no, let's do radians. Degrees, we'd have to go to 360. You'd have to change your windows on your calculators. Radians, you only have to go to 2 pi, which is, what, Joe? Was it a useful question? What? What do you want to use, though? I can't hear the word you're saying. What do you want to use? Oh, calzones. I thought I said calculator, but then I could tell it wasn't calculator. I couldn't hear you, Joe. Calzones, kind of. We'll get there. We'll get there. So as we're doing angles, the reason why we're going to do radians, not because of calzones specifically, but because the numbers are small. If you're doing zoom standard in your calculator, right? If you're doing zoom standard, what are the units of your, or the dimensions of your window? Zoom standard, how big does it go? Tens, right? Positive 10, negative 10, positive 10, negative 10, etc. Okay, so if we're doing zoom standard, we're going by tens. Not going by tens, going by ones, but our window includes 10, and 6.28 is in there. That's radians. They're so much easier for graphing, and the numbers are much smaller for us to work with. So if I go to 2 pi, and if I go to negative 2 pi, just to get a few cycles in to figure out what's going on. Joe reminded us of calzones in the sense of, hey, remember, every semicircle we get to go through all the different values. And maybe that'll kind of display here. I'm just going to go ahead and make this go by pi over 2s just to make life a little bit easier. So each of our quadrants are displayed right here. We have quadrant 1, 0 to pi over 2, quadrant 2, pi over 2 to pi. So there's our 1 calzone. And then we have pi over 2 pi, our 2 calzone. Sine is positive in the first 2 quadrants. Sine's always negative in the second 2 quadrants. But here's what to see. Doesn't sine go up to 1? Now, careful. My graph is in. On your calculator, this would be much, 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 much smaller because your 1 and negative 1 is really small. Think of it as zooming in, but only on the y's, not really the x's. Circle time. What's sine of 0? 0. Because sine goes 1, 2, 3. It counts up. 0. And then it's 1/2. Well, hold on. Wouldn't those all like split this up more? Pi over 6, pi over 4, pi over 3. Let's see if we can just like jump axis to axis and get the idea. At pi over 2, what's sine? 1. Good. Then at pi, where does it go? 0. At 3 pi over 2, now it's at And at 2 pi, it's a wave. Now, it should go through 0, 0 if I did it properly. If I was to keep on cutting it by pi over 2s, it would keep mimicking the same pattern. Now, the sine function itself doesn't exactly understand gravity. What do I mean? The sine function itself is just going to keep waving and waving and waving and waving and waving, going up to 1 and down to -1, up to 1 and down to -1. Is that how life really works? Sometimes the pendulum at Griffith Observatory just keeps going. Why? Because up at the very top, I don't remember if it's magnets or a motor, but there's something that keeps it going. Yeah, a big, huge one. A big, huge one. But do ripples in ponds ever ultimately stop? Or at least fizzle out? Right? But what if, let's not go into like, what if we're in a vacuum and those sorts of things. What if you're playing like a sound and you just keep it going? Is that going to diminish? No, if you play one, I mean, if the battery runs out, but otherwise, isn't it going to be kind of like this in the sense of it has the exact same? Now, what can make the sound waves change? If you hit something, that's gonna disturb, right? I mean, if it's music, then of course they're different notes played at different, frequency. Go in that direction. I was thinking different notes played at different. Yeah, it's not working. Louder and softer. There we go. Just use that. Yeah, it's not where I was going though. Anyway, because if you listen to a song, you guys have watched on, I don't know if it's Spotify, do they even have it anymore? iTunes used to have it. It was a great example because you could actually show like work where it was showing the sound waves and amping up and then going quieter, etc. I think it was called equalizer or something like that. But anyway, coming back. In life, most waves don't just keep going the exact same way, right? Like even heartbeats, we could go there, but that gets a little bit more complicated. It's not always the exact same high and low and continuing on forever. But this is the basic math that we can use to get towards those real-life examples. For instance, grab out your calculators, be in radian mode. I want you guys to graph this following function. We won't really see this until the end of 4-5. It won't happen until Monday. The end of 4-5, which won't happen until Monday. Ooh, so we're not finishing this section today? No. I want you guys to graph the following in your y1. y1 is equal to, hold on, I have to think about it. Let's do 10th e to the negative x sine of x. 1/10 e to the negative x sine of x. Now, I would love to pull up my calculator. Sadly, Ti and I are in a bit of a debate as to why my calculator is not working right now on my program, but that's okay. What do you guys see as you graph it? It's just a straight line? Are you guys in radian mode? It's really big the whole time? Oh, and then it gets really small? So wait, is that wave staying the exact same height the whole time? Is that wave staying the exact same height the whole time? I go ahead, if you were able to zoom, it's a little bit awkward how to get the zoom to work. Can I show you what happens? Sine starts in the middle. Why is it doing this? And why is it doing this? Because it's bounded by, this is what math does. It's bounded by an e to the negative x curve on one side, and it's bounded by a negative e to the negative x curve on the other side. By this guy on one side, and it's bounded by this. Sine curve is different, but mathematically, I can put another function in the Now, it's not showing up in your calculator because you guys didn't graph this as your y2 and your y3. If you did, though, you would see that these guys are actually bounding in this sine curve. And so this guy is making him change. Anyway, cool stuff that can happen that makes it more realistic in the sense of a ripple that would eventually fade out, et cetera, et cetera. But what we're doing right now is just getting the basics of, hey, a sine's a wave? Cool. We can use sine to be a wave? Yeah. We might need to add some more mathy stuff to make it practical, but let's get the idea down of what's going on. Isn't cosine similar in that he cycles? And he cycles between 1 and -1? But what's different about him is he will not be at the exact same place because sine and cosine only intersect or only are the same at what angle? Do you guys remember when sine and cosine are the same? 45s, right? Which would happen halfway in between 0 and pi over 2, if you guys remember, right? So halfway in between 0 and pi over 2, they're both going to be right about here. Sine's on the upswing and cosine's on the, doesn't cosine start below? Yes. 1, 2, 3 is sine. 3, 2, 1 is cosine. Cosine starts at 1. Starts, if you want to think, maximally displaced. And then it goes on its wave's way. So if you want to think about it, a cosine is kind of like a pendulum. It doesn't start in the middle. It starts way over here. And it goes through the 0 as it goes towards the negative and as it comes back. Now I'm going to go ahead and do the same thing over here. And Jordan has your calculator, Priscilla. There you go. I think that positive 2 pi is a little bit closer than the negative 2 pi. It's all right. We're pretending. But ironically, if I take this cosine curve, oh man, that's even worse than the first one. No, but for the illustration I want to show, the closer it is, the better. Because what I'm trying to show is that the sine and cosine wave is practically the same thing. It just occurs in a different way. So if I was to pull this up, guys, they're the same wave, just cosine is shifted a little bit to the left. Sine and cosine, ultimately, if I was to do this perfectly, they're the same wave, which is why we call both of them the exact same shape. They're both called sinusoidal curves, or you could say waves. Sinusoidal curves or waves. You can think it's kind of built on sine. Maybe it's just a way to make you sound like you're from Jersey. Sinusoidal curve. Anyway. Sinusoidal. Yeah, say it a few times. It's fun. But anyway, sines and cosines, sinusoidals. But really they're waves. They're just waves that have a set amplitude. They oscillate. They're cyclic. They have different cycles that repeat every certain set periods. Oh my goodness, so much vocab that we probably need to get into. So we have a sine wave, we have a cosine wave. Let's see how much of just the introductory stuff for this guy that we can get. Here's the first one. Do you guys remember how when we graphed e to the x and ln of x and, even way back to, what was it? Section 1.2, absolute value and a parabola and a cubic, all of our parent functions. Do you remember how I would say, get a few key points down and then you can just transform those? For absolute value, we had like -1, 1, 0, 0, 1, 1. For the parabola, we had like, what did we do? Like -2, 4, 0, 0, 2, 4. Even for e to the x, we had -1, 1 over e, 0, 1, and then 1e. For ln of x, we had, what did we have? 1 over e was -1, 1 was 0, e was 1. Like we had key points, and then you tried to transform them. If there was like a shift or if there was a stretch, we had key points. The hard thing about waves, well, they're way more complicated, number one. And number two, they don't just have one key point. Let me show you. Each of them actually have 5. But hopefully it kind of makes sense. Because there are 5 key locations or 5 key places that the wave passes through in each cycle. For sine, it goes middle, top, middle, bottom, middle. For cosine, it goes top, middle, bottom, middle, top. We could put snazzy words in there like equilibrium and maximum displacement, minimum displacement, etc. But long story short, each of these, sine and cosine, for one cycle of each, there are going to be 5 key points. And here's the idea. If we have to, when we have to, because we just talked about waves and they can be high, they can be low, music can be loud, it can be soft. To model these different things, we're going to have these waves be able to change. And to change, we're going to have to transform them. And to transform them, we don't have to work with every. What if we just worked with the points? So the key points, they're the intercepts. They're the intercepts. They're the maximums and the minimums. 5 per cycle, sectioning the curve. Because if you guys notice, each of these from beginning to end, each wave from beginning to end, if I put little dashes at each location of a key point, I have 1, 2, 3, 4 sections of my wave. If I put little dashes at each key point, I have 1, 2, 3, 4 sections of my curve. And so we're going to find quarter periods in order to figure out how do I section this into fourths. Because the same way I would decide to go by pi over 2s because it was ideal to have each of my key points. When we transform sine or cosine, we're going to want to know what tick marks do I use. And so we're going to use these key points to help. So one more time, sine of theta, his key points, or his one cycle that gets repeated over and over and over again, is going to start in the middle, go up, down, middle, top, middle, bottom, middle. Cosine, his 5 key points, top, middle, bottom, middle, top. Those are the key points I'm talking about. Now, as you guys come down to this graph, Jordan, I'll take your question in a second. He actually doesn't even need a lot of work. There are graphs or trig functions that aren't super complicated. And so what I'm about to show you with like, oh, stink, stuff can get messy. What I'm about to show you with, oh, stink, stuff can get messy, isn't necessarily required for everything. Because, for instance, can you guys tell me the one transformation that happens to sine right here? Vertical stretch by a factor of 2. So the nice thing is with waves, the pebble was just a little bit bigger. The sound just got turned up a little bit higher. What does that mean? Instead of going up to 1, sine's going to go up to 2 instead. And instead of going down to negative 1, I have no idea, negative 1, sine, that's where it came from, is going to go down to negative 2. And so, I said a word wrong. When we graph this sine curve, I mean, we don't even have to think about what's to come with the craziness. We can say, oh, it's just a sine curve where it starts at the middle. That's just going to go up a little bit higher and go down a little bit lower. So if you know what the normal sine curve is, all you have to do is say, okay, I'm going to stretch them by a factor of 2. So sometimes we don't have to stress 2, 2 too much. No, this does want us to go to negative pi. So I guess I would have to technically, just to follow the directions, keep going. And it also says 4 pi, but that's no big deal because 4 pi just says, well, do another 2 pi, hence one more cycle. How did I know that the cycle or the length it took to repeat was 2 pi? Partially because of a circle and partially because of the original graph I just showed you was 2 pi and there was no horizontal stretch or compression that would change. Do you guys see these? I do want you to write both of these down. I'm going to zoom in on them, but the most important one, to be honest, or the most helpful one is going to be this guy. I'm going to zoom in. Hopefully you vertically stretched your wave and said, he's a little bit taller, a little bit shorter. Not taller and shorter per se, but a little bit more stretched. And then we would say he has a higher amplitude. If you amp it up, you turn it up. If you turn it up, the sound waves grow. But there's a lot more that can happen. Just because we're trying to actually make these and cosines useful to modeling actually whether natural phenomena or whether, oh, stink. Or or other applications of waves or cyclic patterns. I'm going to start filling in what this D and A and B and C over B are, but not in terms of like horizontal shift and vertical shift and stretching and compressing, but in a clue way that's going to help, because these are complicated graphs, and I think the easiest way to graph these waves with all of these transformations is identifying some key parts. Jordan, what's your question as I start labeling? Yeah, I accidentally went too low.
Oh wait, am I answering it? I think I answered.
Did you?
I was gonna ask why then, like the top like was 110 like positive and then the other one was negative, but I didn't realize it's the quadrant. So I was just wondering like.
It's actually because sine goes back and forth between positive and -1. And since sine goes back and forth between positive and -1, it actually kind of ultimately ends up making this guy, both the positive values and the negative values affect it. So it's not really because of him, it's because of him going back and forth between negative. Yeah, it's because sine affects him. That's a better way of showing it, because the exponential curve is the swoop. There we go. And it holds in the sine curve. Limits it, I should say. D. Yes, yes, yes. D is the vertical shift. But we're going to, in our clue phase, identify him as our sinusoidal axis. I'm going to call him an SA, which is going to be at y equals d. Basically, he's the middle of the wave. A is going to be our amplitude. Is going to be our amplitude. Plus A. And our A. From the middle point, from that sign, or I should say middle line, we're going to measure up A to how high the wave can go and down A, or subtract A, for how low it can go. The amplitude is technically the absolute value of A. We just add A and subtract A ourselves. We're not actually looking at the plus or minus in front of sines or cosines for the amplitude. The amplitude is just what's the number. I don't care plus or minus, what's the number. B is a little bit tricky. So A is going to be a vertical stretch. That's the old-fashioned way of saying it. B is going to be, well, here's the hard part. He's the horizontal dilation. Maybe I should say dilation, because sometimes it's stretched, sometimes it's compressed. But do you guys remember that inside parentheses, the horizontal ones, they're always backwards of what we think? A minus shifts us right, a plus shifts us left. A times B dilates it by 1 over B. Aww. A divided by B times it by B. So the horizontal dilation is going to be by 1 over B. But what that means is how long it takes the wave to complete, its period will be affected. Now, B is not its period. The period is found by doing 1 over B times 2 pi. Normally it takes 2 pi. Multiply by the factor or the stretch. You can also divide by B. But that's how long it will take to complete. And then C over B, that helps us find our initial point, where to start, which is ironic because it's at the very, very end of the equation. But the very, very end of equation helps us identify our initial point. He is the horizontal shift. He is the horizontal shift. Now, depending on whether you're with a sine or whether you're with a cosine, sine, you're going to start in the middle at that horizontal shift, and cosine, you're going to start at the top with that horizontal shift, unless it gets reflected. Now, guys, we didn't finish 4-5. That's okay, though. What do you have that you should be spending some time on over break? Chapter 3 corrections. So what's due the Monday we get back? Oh, I said Tuesday. Maybe I'm giving you a little bit of a chance to ask me a last-minute question. Have most of the corrections done. If not all, reach out to an honors kid for tutoring hours because they need to help, or they should be helping you, and I'll see you guys later. Bye. If you want to get ahead on the homework, I am going to post section 3.5. There are plenty, 4.5, of videos online if you want to get ahead for graphing sines and cosines.